In the reversible reaction below, 2 moles each of A and B are added to a 1 liter container to start the reaction. At equilibrium, 0.6 moles of C are measured. What is the equilibrium constant? In this case right here, we do not know what the substances are, and the fact we have 3A plus B yields reversibly 2C plus D. They are all gases. Typically, in order for these types of reactions to work, we're talking about molarities, but we're talking about more gas molarities. So in all these cases we've been doing here, these all are generally gases. So let's set this up, that we know that we want to start off with our before, we're interested in our change, and we want to get to equilibrium. And so that's what we're dealing with here. So let's take a look. Do we know the amount of A we had before? It tells us we added 2 moles each of A and B, and we had a 1 liter container. We want the molarity. We want to have the concentrations. And so molarity is moles, and for A, it'll be moles of A divided by the liters. 2 divided by 1 is just 2. That makes this easy. So we have a 2 right there. B is the same thing. We have 2 moles of it divided by 1 liter. Gives us 2 for the concentration of that. It says that we're adding just these 2 to start it, and so for C and D, we don't have any concentration. There's 0 of both those 2. The molarity is 0 for these guys. Looking for our final amounts, equilibrium amounts, it tells us that at equilibrium, 0.6 moles of C are measured. And so we take 0.6 divided by the 1 liter, gives us 0.6. So I get 0.6 for C in this case, and this is what I have to start with. It's all the information I have. I want to find the equilibrium constant. To find the equilibrium constant, we have to know the equilibrium concentrations. And right now, we only know C. So our next step will be saying, all right, what is the change in C? C started off at 0, ended up at 0.6, and since it started at 0 and ended at 0.6, that means the change must be 0.6. And so that's going to be our change in C, and it's going to be plus 0.6. It's positive here, which makes sense because we expect that when this reaction started off, entirely weighted to the left side with A and B having stuff but C and D not having anything, and so this reaction is going to flow right. So we're going to see positive changes for C and D. We're going to see negative changes for A and B because it's flowing away from A and B. So let's look at what we got set up here. Let's look at D because we know it's going to be our other positive one, so we know it's going to be positive right here. But we got to figure out what the change is going to be. Well, let's look at the mole ratio between C and D. C has 2, D has 1. So that means that the mole ratio from C to D is going to be a 2-to-1 mole ratio. And so we will have half as much D as we do C. And so in this case, instead of being 0.6, it'll be half of that, 0.3, because that would be a 1-to-2 mole ratio from D to C. And so that works out there. For A and B, let's take a look at B first, because it looks a little simpler here. The mole ratio from C to B is also a 2-to-1 mole ratio, and so it's going to be 0.3 as well. Only in this case, it's going to be negative 0.3 because, once again, it's flowing away from that A to B side. That's where it started. It's going to flow away from it because, well, it can't flow from right to left because it had there's 0 concentration to start with on the right side. So we've got that. Now for A in this case right here is their 3A to 2C, so that's a 3-to-2 A to C ratio. And so if you work out that ratio here, as we know that that a 1 would be 0.3, and so based on what we found before here, and so we have 3 times that for A, so that'll be 0.9. And so it's going to subtract off 0.9 here. And once we've got that, now we can go ahead and figure the equilibrium concentrations. 2 minus 0.9 is 1.1. 2 minus 0.3 is 1.7. We've already got the carbon, the C, and then D, 0 plus 0.3 is 0.3. Now we have all the molarities of each of the concentrations at equilibrium. All the concentrations in molarity at equilibrium. The question is, what's the equilibrium constant? And so to find KEQ, remember that we want to take the concentrations of the right side first, and so that's going to be 0.6 for our first one for the C, and since its coefficient is 2, it's going to be 0.6 squared, times the concentration of D, which is 0.3, which has no coefficient's 1, so it's just 0.3, divided by, let's look over on the left side, because the left side's always on bottom when you're solving for KEQ, and we have a concentration of 1.1, and that one is, since the coefficient's 3, it'll be 1.1 to the 3rd power, times the concentration of B, which is 1.7 at equilibrium. And that one is, since the coefficient of B is a 1, it's just 1.7. And now it's just basically go ahead and do the math on it. And so when we're setting this up, we say 0.6 squared times 0.3 then divided by on the bottom 1.1 cubed, and then divided by 1.7. And when we do that, I get a KEQ of 0.0477. 0.0477. For significant figures, we have 2 moles up here, and so that's only 1 sig fig, and so that went into our calculations here. And so our final answer here would be 0.05 would be our final value of KEQ that we get right here. And that's how you'd go ahead and use that mass action expression to go ahead and find an equilibrium constant. 5 moles each of A and B were inserted into a 20-liter container to start a reversible reaction. If KEQ equals 4.2 times 10 to the negative fourth, what are the equilibrium concentrations of each substance? So our reaction is 2A plus 3B is reversible to C. And so we want to set this up the same way we did the other ones before. And so we have a before, we have a change, and we have an equilibrium amount. All right? And so we're told that we have 5 moles each of A and B to start off with here in a 20-liter container. We need to find the initial concentrations. And so for the initial concentrations here, we say we have 5 moles divided by 20, and we do that, we get 0.25. So my before concentration of A is 0.25, my before concentration of B is 0.25, my before concentration of C is going to be 0 because I didn't have any C to start with here. All right. So, do we know anything about the equilibrium concentration? Not a 1. We don't have any information about that. And so what we're going to do is we're going to call the change basically X for one of these substances. And in this case right here, A has a coefficient of 2, B has a coefficient of 3, C has a coefficient of 1. Since C has a coefficient of 1, we're going to call the change in C X. Okay? Now, since the fact that this reaction starts on the left because we have 0.25 of both of them to start with, is that we can set this up this way. It's going to go from left to right. That means this is going to be positive X. Okay? That means that the change in B, we start off at 0.25 for the concentration, is going to have to be in mole ratio with that X change that we had for C. And so C has a coefficient of 1, B has a coefficient of 3, and so that's going to be a 1 to 3 ratio. And so if C gained X, B is going to lose 3X, like that. And A, since it's got a 2 to 1 ratio from A to C, if C gained X, A has to lose 2X. That should sort of make sense for right now, is that we don't know what it is, but we know they have to be in that ratio of a 2 to 3 to 1 ratio because the coefficients are a 2 to 3 to 1 ratio. So, do we know what the equilibrium constants are? Not the numbers for them, we do know them in terms of X. C is going to be just X, so 0 plus X is X. B, though, is going to be 0.25 minus 3X. For it, the equilibrium concentration for A is going to be 0.25 minus 2X. Ooh, we don't like that, but that's what we've got for right now. Question is, what are the equilibrium concentrations for each substance? And so we know the equilibrium concentrations here. We know that KEQ is 4.2 times 10 to the negative fourth. Now, let's set this up by solving for KEQ in terms of X. And so we know KEQ is 4.2 times 10 to the negative fourth. So 4.2 times 10 to the negative fourth. And this is going to equal to the ones on the right. There's only one that's on the right here. That's our X. And so we have X on top, our concentration X that's right there. It's raised to the power of the coefficient. In this case, that's just 1, divided by the guys on bottom. And so the first one that's on bottom will be the first one that's on the left. And so that's going to be 0.25 minus 2X raised to what power? Raised to the second power. I'll continue that over there. Then also divided by our B concentration equilibrium, which is 0.25 minus 3X to the coefficient there, which is 3 to the third. Oh boy. Could we solve this? Actually, we probably couldn't. Just by doing the math straight up here. Because the problem we run into is, I mean, if you look at this, if we multiply those two terms on the bottom, we're going to get something that has an x to the 5th power. And so we're going to end up with basically a quintic equation here, and you don't have a way of solving quintic equations for x. You could do a quadratic equation, and there are methods for even solving cubic equations, but anything above x to the 4th power, there's no general way to find the solution. And so it sort of seems like we are stuck a little bit here, except for one thing. Remember that we said that in order for get this technique to work is that if your equation started on the left, that you needed a KEQ that was very small. In this case right here, our KEQ is 4.2 times 10 to the negative fourth. This is a very, very small value of KEQ. And if you also remember our definition of KEQ, we said that when KEQ is small, it means the reaction favors the left side very heavily. And if this reaction favors the left side very heavily, since it starts off on the left side, it means there won't be a whole lot of change. That means X is very, very small. Whatever this change is, it's got to be tiny. And if X is very, very small, then we can do a little bit of an approximation. Because let's look at this term that's on the bottom here. We have 0.25 minus 2X. If X is tiny, like 0.00001 or something like that, then 0.25 minus a really tiny number is basically the same as just having 0.25. And so the same thing is true over here. If X is a very, very tiny number, then 0.25 minus 3X, if X is really tiny, is basically the same as 0.25. We can basically do an approximation here. And if we do this approximation, then we can rewrite this a little bit. So we say 4.2 times 10 to the negative fourth is going to be equal to X over, but in this case we've done our approximation. Our approximation is 0.25 times 0.25. This one we can definitely solve. And so note that we can't go ahead and assume that top X is going to disappear because it's by itself. This is only something that works comparatively, is that that 0.25 minus 0.0001 is basically 0.25, but that's not the same as saying 0.0001 divided by something is the same as 0 divided by something. Those aren't true at all. This only works whenever we've got something minus something else or something plus something else. But going ahead, we can go ahead and solve the one we've got up here at top, and so we'd say 0.25, oops, I forgot something here. It's 0.25 squared here and 0.25 cubed here, because remember these coefficients are still there. And so we'd say 0.25 squared times 0.25 cubed in this case, or you could have just done 0.25 to the fifth in both cases. Then we're going to multiply that up. So times 4.2 times 10 to the negative fourth. And so if we do that, we get something that's a really, really tiny number. And so in this case, let's see if I can count my decimals over. 1, 2, 3, 4, 5, 6, 7. So I get that X is equal to 4.1 times 10 to the negative seventh. And if that's true, then is it reasonable that I would have ended up, that my assumption here is 0.25 minus 2 times 4.1 times 10 to the negative seventh, basically 0.25. Most definitely. It's basically going to be 0.2499999. I mean, it's going to be some incredibly number. It's very, very close to 0.25. This is a reasonable approximation to make. And if this is the case, the question is, what's the equilibrium concentrations of each substance? And so here is that we started off here with the equilibrium concentration of A was 0.25 minus 2x. Well, 0.25 minus 2x is basically going to be, since x is so small, 4.1 times the negative seventh, is basically 0.25 molar. For our second one, 0.25 minus 3x, it's going to be the same thing. It's going to be 0.25 molar in this case, because that's basically the same thing. But for our last one is just x. X we just found is 4.1 times 10 to the negative seventh molar. And so because of the fact that KEQ was so small that we could basically work out all our answers here, and I guess technically we probably ought to, since this was 20-liter container, we should have rounded this to 1 unit figure, so it probably should be 0.3 molar, 0.3 molar, and 4 times 10 to the negative seventh. But you get the basic idea on how this sets up. What you want to do in this case is set up the equation the same way we had before, only with our variable x in the place of the change set to the mole ratios. And then once you've written out your KEQ equation, you want to look for cases where that your value of KEQ is going to let you do an approximation. It's going to, if your x is either going to be very, very small in some cases, well, it basically will be very, very small. And with that very, very small x, things that are differences like 0.25 minus 2x or 0.25 minus 3x, you can basically approximate to be just like the 0.25 here. So let's try out another one of these to make sure we get a little bit of practice on this. And it works very, very similar to this last one, and get a little more practice on it. All right. In a reaction with an equilibrium constant of 2089, 0.3 moles of CO2 is added to a 10-liter container to start the reversible reaction below. What are the final concentrations of carbon monoxide and oxygen gas. So we have 2CO plus O2 reversibly yields 2CO2. And so we're going to set this up the same way that we have before, in that we want to have our before, we want to have our change, and we want to have our equilibrium position here. And so what do we know to start with? We have 0.3 moles of CO2 that are added to start the reversible reaction here. So we have 0.3 moles as the number of moles. The container is 10 liters, though apparently I can't tell the difference between a 0 and an O on my keyboard. So that gives us 0.03 for the concentration of CO2 to start with. So we have 0.03 molar carbon dioxide to start with here. It says we're starting by adding this. That means we have no oxygen to start with, no carbon monoxide to start with. And we likewise have no idea what we have for our equilibrium concentrations. And that means we don't know what our changes are either. We do know that since we started off with 0.03 molar stuff over here, is that this one is going to go, since it starts off with 0.03 molar on the right, this one is going to have to basically start off by going left. And so that means that the carbon dioxide is going to lose, and the carbon monoxide, the CO, and the oxygen are going to gain in their change. Of the three things, we have two carbon monoxides, one oxygen, two carbon dioxide. So our change here we'll probably do the oxygen first because it's got a 1 for its coefficient. And so its change is going to be X. We're going to add X on this one. And since the mole ratio from oxygen is 1, for carbon dioxide is 2, so it's a 1 to 2 ratio here. This will be 2X for this guy right here. And then for our last one, our 0.03, is that we know it's going to end up being, since that's got a 2 for the coefficient, it's a 1 to 2 ratio, it'll be minus 2X. So for our final concentrations, we have 2X for carbon monoxide, X for oxygen, and 0.03 minus 2X for the carbon dioxide. So let's go ahead and let's set up our equilibrium equation. Our equilibrium constant equation. So we have 2089 is our equilibrium concentration, is equal to the things on the right. On the right now we have 0.03 minus 2x raised to the coefficient, which is 2, second power, divided by the things on the bottom, which are carbon monoxide, which has a concentration at equilibrium of 2x, but since its coefficient is 2, it'll be 2x squared. And then the oxygen has a concentration of X. Since it's just a coefficient of 1 out front, it's just X by itself. Once again, we probably really don't want to have to solve this. Let's see if we can use one of our tricks here. Well, we know that the equilibrium constant is 2089. It's not small like the last one, but unlike the last one, this guy right over here starts on the right side. And we know that the rule is that if your reaction starts on the right side and your equilibrium constant is large, we can use our trick here. Because if the equilibrium constant is large, that means the reaction wants to stay on the right side. And if it wants to stay on the right side, that means X is once again going to be very, very small. And if X is very, very small, then it means that our little trick right here, 0.03 minus 2X, if X is very small, then it means that that is basically the same as just having 0.03. And so this is going to be our little trick here, because if X is small, and it has to be if it's going to have a very large KEQ, then basically this is equal to just 0.03. And so we can rewrite this guy as 2089 is equal to just 0.03 squared divided by, on bottom we have 2x squared, which is 2x quantity squared, which is just 4x squared times x. So that would be 4x cubed on bottom. And so at this point, we can just sort of solve for x. Let's multiply x up. And so we have 2089 times 4x cubed. And so that ends up being 8356. X cubed is equal to 0.03 squared. And so divide both sides by 8356. 8356. And so when we do that, we say 0.03 squared divided by 8356. And I get that x cubed is equal to, let's see, I got to count here. 1, 2, 3, 4, 5, 6, 7. 1.08 times 10 to the negative 7th. And then I got to take the cube root of that. So raised to the 1/3 power, or just take the cube root if your calculator does that. And so in this case right here, I get x is equal to 0.00475. We have 0.3 moles to start off with this one here. 10 liters, all one significant figure. So our answer right here would be rounded to 0.005 would be my x value here, is what I get for that. Now for my x, but the question asks for what the final concentrations are. And so if this is the final concentration here, we got to find them for all ones. So for the carbon dioxide right up here, it's 2x is what that is. We got that right here. And so for the concentration of the carbon monoxide is basically going to be equal to 2 times this guy right here. So times 2. And so for that concentration, they just basically get 0.0, actually be 0.0095, which since it's one significant figure would be 0.01. Okay, molar. For the oxygen's concentration would be just x, so that would be 0.005. Okay, molar. For our last one here, the CO2, well, we said x is very, very small here. And so it would be basically 0.03 minus 0.005 times 2. 0.005 times 2 is 0.1. And so for our last concentration, for our carbon dioxide concentration, CO2, if I can get that to fit in here, is basically going to equal to 0.02. is what we get here. This one's probably pretty borderline about being able to use this technique, because you see that x was decent size compared to the 0.03 at the very end. It did reduce it by about 1/3 here, but and it does tend to, the closer that you get to a reasonable size, the farther off this deviates from being perfect. But this technique works pretty well if you have a case where you're trying to solve for an unknown and you really don't have enough information to use it. If these two things are true, that you have an equilibrium constant that's either very small and it starts off on the left, or it's very large and it starts off on the right. But this is basically the technique that you use. One of these two guys, either using the technique we started at the beginning of this lesson or this one right here, will both get you through to what you're looking for here.